You ever look at the periodic table of elements and just stare at it for a second? I mean, why is it shaped like that? It's not a nice, neat grid. It's got these weird blocks, these big gaps, and then that whole chunk just kind of floating at the bottom. Well, turns out that weird shape isn't random at all. It's a secret code, a fundamental blueprint that basically runs our entire universe. And today, we're going to crack it.
Okay, let's make this real. You've probably got your phone with you, right? Well, that little battery inside, it runs on a tiny, super lightweight element called lithium. And the secret to why lithium is so good at powering your phone is the very same secret that explains the whole shape of the periodic table. It all boils down to one simple thing. It's incredibly reactive.
And I mean, this stuff is a powerhouse. It's in everything. Laptops, cameras, even pacemakers and the batteries in electric cars. All of its usefulness comes directly from that high reactivity. And that reactivity is decided by just one thing: the way its electrons are arranged. And that right there is the key we're about to unlock.
So, here's the game plan for today. We're going to start with that secret in your battery, and then we're going to learn the actual elemental code that organizes all atoms. From there, we'll build the periodic table ourselves, check out a few weirdos that seem to break the rules, and finally, see the incredible power this pattern gives us.
All right, let's jump right in. Part 1, a secret in your battery. We're going from something you can feel, that reactivity in an element like lithium, straight to the cause, its atomic structure.
So here is the absolute most important thing to get. The periodic table isn't just a boring chart of cosmic ingredients. Think of it like a map. And what it's mapping is the arrangement of electrons in every single atom. An element's entire personality, how it behaves, what it bonds with, if it's a metal or a gas, it's all dictated by those electrons. And if you know how to read this map, you can predict what any element is going to do.
Okay, so let's get into the code itself. Section 2, the elemental code. You're about to learn the surprisingly simple rules that tell every single atom in the universe how to organize itself.
To really get this, let's use a great analogy. Picture an atom, like it's a giant concert hall. The nucleus, with its positive charge, that's the stage. That's the main event. The electrons, they're the audience. And you know how it is at a show, right? The best seats, the ones with the lowest energy, right up close to the stage, those are the ones that are going to fill up first. This best seats first idea is our very first rule. It's got a fancy name, the aufbau principle. It's German for building up. But all it really means is that nature is efficient, kind of lazy, in the best possible way. Atoms always fill those low-energy seats first before they even think about moving to the nosebleeds.
Now, our second rule is pretty much just basic politeness, but for atoms. Think about getting on an empty bus. You don't go sit right next to the one other person on there, do you? No, you find your own row. Well, electrons do the exact same thing. In a row of seats that all have the same energy, each electron takes its own spot before anyone starts pairing up.
Okay, so let's put our concert hall rules together. Rule 1, fill the best seats first, close to the stage. That's the aufbau principle. Rule 2, in a row of equally good seats, spread out. Everyone gets their own seat before you double up. That's Hund's rule. And one last little detail, each seat, or orbital, can hold a maximum of 2 electrons, but they have to have opposite spins.
And now, for the really cool part. Section 3, building the periodic table. We're going to use these rules to build the first few rows of the table from scratch, and you're going to see that famous, weird shape just emerge all on its own.
We're going to start with the simplest of all, hydrogen. It has just 1 electron. So, following our rules, where does it go? The best seat in the house. The very first spot in that lowest energy level. That's it. Simple.
Next up, helium. It has 2 electrons, the first one takes a seat, and since that level can hold 2, the second electron just pairs up right next to it. And just like that, the first energy level is completely full.
And here we are, back to our friend lithium, with 3 electrons. Okay, so the first 2 fill up that first level, just like in helium. But that level is now full, so the third electron has no choice but to start a brand new level, all by itself. And that is the secret to its reactivity. That one lonely electron sitting way out on the edge is super easy to give away. That's what makes lithium so eager to react with other things.
Okay, let's jump ahead to carbon, the foundation of all life. After the first 4 electrons fill their seats, we've got 2 left. Now, remember that bus rule? They don't pair up. They each take their own separate seat in that next row of orbitals, giving themselves a little personal space. And finally, let's look at neon. With its 10 electrons, it perfectly fills every single available seat in its first two big energy levels. Everything is paired up, everything is complete and stable. This is what makes neon a noble gas. It is perfectly happy, totally content, and has absolutely no desire to interact with anyone.
And here is the big aha moment. This is the reveal. Just look at the elements in the same vertical column, what we call a group. In group 1, hydrogen, lithium, sodium, they all have that exact same single electron in their outermost shell. And over in group 17, fluorine and chlorine are both just one electron shy of having a full shell. This is it. This is the reason. Elements in the same column act like family because their outer electron configurations are identical. The shape of the table is a map of these electron families.
So now we get the rules that build the table. But, sometimes in chemistry, atoms will bend those rules, but they always do it for a really good reason. So let's get into section 4, stability and oddballs.
So, check out the element chromium. If we just follow the rules we've learned, we'd expect its electrons to be arranged in one specific way. But when we look at it in nature, we find something a little different. It looks like the atom actually promoted one of its own electrons from a lower level to a higher one. The atom is cheating. So, why would it do that?
And the answer comes down to the one rule that trumps all the others. Nature always seeks stability. It just so happens that there is this special kind of Zen-like stability that an atom gets when its rows of seats are exactly half full or completely full. So to get to that more stable state, chromium bumps one of its electrons up. It breaks a little rule to follow a much, much bigger one. Find the most stable, lowest energy state you possibly can.
And chromium isn't alone here. Copper does the exact same thing, but it does it to get a completely full outer subshell, which is an even more stable arrangement. See, these exceptions don't actually break the system, they just reveal a deeper layer of the rules, that overwhelming drive for stability.
Okay, let's bring it all home in our final section and see why this all matters so much. Section 5, the power of the pattern. What does cracking this elemental code actually let us do?
Well, it explains pretty much all of modern chemistry. Seriously, it explains why we have chemical families. Elements in the same column act alike because they have the same outer electron setup. It explains why ions form the way they do. Of course, calcium easily loses its two outer electrons. It wants to get to that more stable, full shell configuration underneath. This code even explains things like magnetism. Iron is magnetic because it has a bunch of unpaired electrons all spinning in the same direction, just like Hund's rules said they would. And that right there is the real power of understanding this code. The periodic table isn't just a static chart on a classroom wall. It's a dynamic blueprint for matter itself. When we understand these fundamental rules of how electrons arrange themselves, we don't just explain the world as it is, we get the ability to engineer it. Which leaves us with a pretty incredible thought. Now that we've cracked the code of the elements, what new materials, what new medicines, what new technologies are we going to design with it?